And for our second talk, we have Andrew Berget from Western Washington and IAS speaking on the external activity complex of a pair of matroids.
Thanks everybody for coming and talk. We're happy to be here today. We'll tell you about my results. This is joint work, everything with Alex Fink. So the plan for my talk today is I'm going to give you two motivating problems, and then I'm going to give you two combinatorial constructions, which I feel totally unrelated to the motivating problems. In the third part of the talk, I'm going to tell you my results, which connect the combinatorial constructions to the motivating problems and solve one of the motivating problems completely. And then in the last few moments, I'll give you a small epsilon of details. So I am going to give a talk in the special year seminar in 2 weeks. And I should say that I've kind of ignored the algebraic geometry background that goes into all of these results. You kind of feel it running under the hood, but I'm not talking about any of that today. So if it's a very, very beautiful story. And so if you want to learn more, please the special year seminar. So my first motivating problem concerns the hypersimplex. So the hypersimplex, I'm going to denote sigma Rn. It's the convex hull of the indicator vectors of the size R subsets of the numbers 1 through n. This is the convex hull in Rn. So this polytope, it always lives in a hyperplane where the sum of the coordinates is equal to R. And so it always ends up being an n-1 dimensional polytope. And so here's a picture of the 2,4 hypersimplex inside of R4. It's a 3-dimensional polytope. And here I've labeled all the vertices of the polytope by the 2-element subspace that they correspond to. I'm also going to need to talk about matroid-based polytopes. So throughout the talk, M is going to be a matroid of rank R on the numbers 1 through n. I'm going to think about all different things associated to the class circuits, its bases. Here, the matroid-based polytope is going to be the convex hull in Rn of the indicator vectors of the bases of the matroid. Okay, so there's a famous theorem of Gelfand, Goreski, McPherson, and Serganova that says that a polytope that's contained inside of the hypersimplex is a matroid polytope if and only if it comes, its vertices are all vertices of the hypersimplex and all of its edges are edges of the hypersimplex. So here's an example of, so on the left, we've got the 2,4 hypersimplex, and on the right, I have a matroid-based polytope, which is just the top pyramid within this thing. So all of its edges, all of its vertices are all vertices of the hypersimplex, and all of its edges are edges of the hypersimplex. So the matroid that's associated to this polytope on the right is a parallel extension of uniform rank 2 on 3 elements. Okay, so the next thing I need to state this motivational problem is we need to talk about subdivisions of the hypersimplex into matroid-based polytopes. So by this, I mean a polyhedral subdivision of a hypersimplex, and I want all of the with no new vertices. And and I want to require that all of the faces involved in this subdivision are all matroid-based polytopes. Okay, so on the left, once again, we've got the 2,4 hypersimplex, and on the right, we have really, so this is the only example that you can draw And we've got a subdivision of this thing into Matroid-based polytopes. I've got the pyramid, square-based pyramid on the top, square-based pyramid on the bottom, and those are intersecting along a common face, which is also a Matroid-based polytope. So the thing to know here, or to notice here, is that there are two three-dimensional pieces involved in this subdivision, and there is a single two-dimensional piece involved in this subdivision. So in 2004, David Speyer was investigating tropicalization of the Grassmannian, and the study of regular subdivisions of the hypersimplex arises quite naturally in that study. And so those are going to be polyhedral subdivisions that come from lifting the vertices of the hypersimplex into one dimension higher, looking at the lower convex hull, projecting back down. And motivated by this, David conjectured an upper bound on the number of faces indexed by their dimension that can be involved in so internal faces that can be involved in a Matroid-based polytope subdivision of the hypersimplex. And so he said that they are bounded above by this product of binomial coefficients. He also actually gave a criterion for when equality occurs here, which is when the polytope, so the hypersimplex is subdivided into the base polytopes of series parallel matrices. Okay, so here's an example when R is equal to 2 and N is 4. David conjectures that there's at most two three-dimensional pieces and a single two-dimensional piece. And so what this means is that the subdivision that we had on the previous slide somehow achieved equality. So David was able to prove this, this conjecture in the case when all the polytopes involved in a subdivision are all come from realizable matroids, matroids that are realizable over the complex numbers. Okay, so this is the end of the first motivational problem. There's any questions here?
Is there any assumption of regularity?
No, just any subdivision. Okay, so my second motivational problem is a priori feels totally disconnected first. So I need to set up some notation here. So Xn is going to be the permutahedral variety. So this is the torque variety that is associated to the it's what the torque variety associated to the fan that is the normal fan of the permutahedron, which is the convex hull in Rn of the all permutations of the numbers 1 through n. So this polytope also lays inside of a hyperplane where the sum of the coordinates is constant. And so this ends up being an n-1 dimensional torque variety. And in spite of this, there's actually a natural action of an n-dimensional torus, so that I'm going to denote by T. So T acts on the permutahedral variety, and it acts with a dense orbit. Okay. So I also need to tell you about an action of the this same torus T on n-dimensional affine space. And so this is like a minor technical detail, but so what I want is the ith factor of my torus T to act on the ith factor of Cn by inverse scaling. Okay, so in joint work with Christopher, Hunter Fink, and Dennis Seng, we investigated some vector bundles that are associated to linear spaces, and so I want to tell you how to construct these vector bundles. Okay, so what you're going to do is you're going to fix a linear subspace of Cn, And what we can do is we can construct a unique subbundle of the trivial bundle. So the trivial bundle given to us by Cn, the described torus action. And so in order to tell you what this vector bundle is, it is sufficient to actually tell you what the fiber of the bundle is over the identity of the dense torus of the permutahedron. And equivariant bundle. Yeah, so what if I tell you what the fiber is over the identity, then I can smear it out to fill up the to all the other fibers. And so what I want is the fiber over the identity to actually be this subspace C, or sorry, L. Okay, so this describes for me what we call the tautological subbundle associated to the space. There's also a tautological quotient bundle associated to the linear space, which is just Cn modulo the tautological subbundle. Okay, so we've got these vector bundles. These, there is a generalization to all matroids, but it's not the bundles themselves that generalize. It's their K classes. So I'm going to let K naught of Xn. So this is going to be the growth and deep group of vector bundles on the permutahedral variety. So this is going to be isomorphism classes of vector bundles modulo that come from short exact sequences. And it turns out that the classes of the tautological subbundle and the tautological quotient bundle, these depend only on the matroid of the linear space that you started with. And there is, in fact, a way to sort of uniformly generalize the description of the classes of SL and QL to any matroid. Okay? And so the generalizations possess many beautiful properties. And so here's my second motivational problem. The first one is a geometric problem, which asks if you can compute higher cohomology of these vector bundles. Yeah.
Sorry, what is this matroid ML?
So if you have a subspace of L is a subspace of Cn, then you can construct a matroid from this by looking at the coordinate functions on the coordinate functions of Cn, and you restrict those to the linear space. And that gives you some linear functions on L, and then you remember whether those are independent or dependent. There's something, I mean, there's like a simpler way to say it. If L is the row span of some matrix, then the matroid is just the matroid given to you by the columns of this matrix. Okay, so my first motivational problem is a geometric problem, which asks for the higher cohomology of these like certain vector bundles. So I want to look at tensor products of exterior powers of dual quotient bundles of different linear spaces. So this is like a big problem. And I mean, so like and of course, like higher cohomology of vector bundles, like I mean, already seems like an extremely daunting task. It's not clear that these higher cohomology groups will even that they depend only on matroid data, and there's actually some evidence that they might not. Okay, so that's but maybe we can just ask, can we say when there is some vanishing of these higher cohomology groups?
Why do you look only at duals?
So first of all, if I want to erase the duals, then you can just take the AIs to be negative. Okay, so But I should say that like, there's, at least in characteristic zero, I'll say something on the next slide. Okay, so my second problem is, so this is an entirely combinatorial problem, and it has to compute the Euler characteristic of tensor products of exterior powers of dual quotient bundles of different matroids. Okay, and this also seems like a really daunting, challenging problem. Can we just say something about what the sign of these Euler characteristics is? So here's some partial progress.
Why do you know that? What's combinatorial?
Well, oh, sorry. Okay, so this is combinatorial precisely because, I mean, the classes themselves only depend on the matroids. And the Euler characteristic is just the, I mean, so that's just a function from K naught to the integers. It's the linear extension of like the Euler characteristic of an actual vector bundle to all classes.
What's the difference between 1 and 2 there? I don't.
One, so 2 is, at least for realizable matroids, it's the alternating sum of the things that show up in 1. 2 is manifestly a combinatorial invariant. 1 is not, but it could be that the dependence on the linear spaces themselves sort of cancel out when you do the alternating sum.
It will be the dependent that linear spaces cancels out when you do the alternating sum,
Yes.
because Euler characteristic is well defined on three classes.
Okay. Other questions?
But do you have an example where 1 changes for different realizations, or?
So Matt has some example that suggests that they are different, and in fact, it would probably be. I'm actually extremely interested to see if we can actually find one more.
I think the answer is they are different.
Okay, they are different. So, but this sort of gets to Leo's question, which is that I have reason to believe that if all the AIs are positive or all the AIs are negative, then I believe that the higher homology does not depend on realization, but Matt might not agree.
What is wedge -1?
It would just be erase the dual. It'd be wedge 1 with no dual.
But ordinarily, you wouldn't expect like both the vector bundle and its dual to have the energy.
Oh, so yes, you are correct. Okay, so yeah, sorry, this thing, like the clicker doesn't advance. So in that case, yeah, I would change the question then and just say describe the higher cohomologies. Okay, so I believe that the higher cohomologies, if all the AIs are positive, does not depend on the linear spaces, only the matrix. Yes.
And what kind of answer to for the characteristic you would want?
Okay, so that'll be one of the main theorems today. I'll show you what I accept, what I want is good. Okay, so here's some partial results here. In 2010, Alex Fink and David Speyer, they proved vanishing of the Euler characteristic of some tensor product of exterior powers of a single matroid. Okay, so same M in on both bundles. And so I'm not gonna write make a distinction between the class SM versus so I'm gonna drop the brackets that go around it. So it just gets kind of burdensome. Okay, so
That's before like S and Q were introduced.
yeah. What? Sorry.
Things how you're speaking.
Yes, but it turns out that it's sort of fine. You just pull back from the torus orbit closure and the Grassmannian to the permutahedron by resolution of singularities. It's no big deal. Okay, so Alex Fink and David Speyer proved this vanishing that I've displayed here when P is not equal to Q. And I mean, they proved a lot more things. But one of the things that they also showed in this paper was that if you're able to say the sign of the displayed Euler characteristic when P is equal to Q, then you can actually answer David's F vector conjecture. Okay, so then in later in 2018, Alex and I proved that there's vanishing of all the higher cohomology groups when you do a tensor product of exterior powers of quotient bundle of L. So here there's no dual. We needed to assume that we were working in characteristic zero. Chris recently has a paper where he shows that there's no higher cohomology. So now he can just do this for a exterior power of a dual quotient bundle, but he removes the characteristic hypothesis and he does it for a dual quotient bundle, which is harder than for like QL no dual.
Maybe this might be an unfair question, but I wouldn't have expected this last result because I think of Q as sort of positive and Q dual as sort of negative.
Yes, this is a surprising result, but essentially, right. So if you were to, for example, take tensor powers of that bundle, then there's definitely going to be higher cohomology.
Okay, so it's like a Kodai with vanishing that you go a little bit in the negative range. It doesn't happen yet.
Yes, that's correct.
Sorry, just to clarify, so for all of these results, do they hold for all else that arise in a way that you just described, and also as well as for all M?
So this we can't like these two, they technically don't have definitions for like non-realizable matroids. This one works for any realizable L. So any subspace L that's contained in like a framed linear space. And this works for any L contained in C to the N.
Characteristic zero for the third result or any characteristic?
Any characteristic for the last result. Okay, so that's my, I think, oh yeah, so where's my talk going from here? So what I can do is I can give you what I would call a pretty good, but not optimal formula for what the Euler characteristic of a tensor product of two different dual bundles is. And in the case that the matroids are realizable over a field of characteristic zero, then you can actually upgrade this to formulas for the higher cohomology. If you use, so the results of Fink and Speyer from, what was it, 2010, and then some forthcoming results of Alex, David, and Chris Shaw, then you can actually prove that Speyer's F vector conjecture is true. Okay, so that's the last that I'll say about Speyer's F vector conjecture, and so the focus now is just on part one.
Sorry, is H0 like combinatorially interesting then?
So in this case, there's actually going to be higher cohomology. There's probably not going to be H0. The cohomology, I believe, is concentrated in a single degree. And I'll tell you exactly what that degree is. Okay, so we're now gonna start like a totally new part of the talk. So this is gonna be entirely combinatorial. And so I'm gonna give you two constructions. Throughout, I'm going to be starting with a pair of matroids. By a pair of matroids, I'm going to mean a pair of matroids on the same ground set that don't have any loops in common. And like the no loops in common is like a technical assumption. So I'm going to call a subset I of the common ground set, which is the numbers 1 through n. We're going to call it Dilworth if for every element of the ground set, I can add that element into I, and that resulting multi-set should decompose as a union of an independent set from M1 and an independent set from M2. Okay, so the collection of, so you need to be able to do that for all elements of the ground set. So a proposition is that if you look at the collection of all Dilworth sets that are determined by this pair, M1, M2, then that's the collection of independent sets of a matroid, D, M1, M2. There's going to be a lot of examples of this construction because it's central to the problem. So Alex and I call this the diagonal Dilworth truncation of M1, M2. Sometimes I'll just denote it by D, because saying D of M1, M2 can start to be a mouthful. So originally, this was like first introduced by Dilworth in 1944. And what Dilworth was interested in doing was taking a geometric lattice, hacking off like the bottom, like the rank 1 flats in a geometric lattice. The resulting thing is no longer a geometric lattice, and he wants to complete it by adding more stuff to it to form a geometric lattice. And so you want to add things in higher ranks to form a geometric lattice. So, but it turns out that Dilworth's construction is pretty complicated, and we're not going to really understand anything about this matroid D by using that. So instead, it's easier for me to tell you what the circuits of the diagonal Dilworth truncation are. And so the circuits are going to be minimal subsets C with the following property, that their cardinality is equal to the rank of C in M1 plus the rank of C of M2. This is what the previous definition demands. Example. So this is a really important motivating example, which is that if you were to take one of the matroids to be uniform of rank 1, then the diagonal Dilworth truncation returns the other matroid. Okay. So and let's think about this. So if I have an independent set in M2 and I add something to it, then can I witness that as the union of an independent set from M2, union an independent set from uniform of rank 1? Yeah, absolutely. So then you need to show that those are all the possible independent sets. Okay. Some other kind of reasonable things that a person might wonder about this is what happens if you take the diagonal Dilworth truncation of a matroid and its dual. And it turns out that in almost all situations, you're going to get a uniform matroid of co-rank. There are some degeneracies that can happen, so it doesn't always. The other thing to sort of keep in mind is that if the ranks of M1 and M2 are both somehow large, okay, then D of M1, M2 is usually just the Boolean matroid. So this is, it's a little bit strange and perhaps distressing that this construction is mostly interested in two matroids that have a relatively small rank.
Why is it called truncation?
So it's like so these are called like lower truncations because like in Dilworth's original construction. So the truncation of a matroid just like hacks off the flats like in some upper set in the lattice of flats. And so these are the lower truncations where you hack off bottom of the lattice of flats.
The Dilworth truncation in the classical sense is related to this D in what way?
So you take the direct sum of the two matroids, you take the Dilworth truncation, and then you look at the diagonal of the ground set. So like so that's why we call it the diagonal Dilworth truncation. Okay, so there's a construction that's due to Brolowski from 1975 that says that if both M1 and M2 are realizable, then the diagonal Dilworth truncation is also realizable. You sort of can't, this doesn't give me a huge amount of intuition, so I didn't include the construction here.
What doesn't follow from what you just said?
Sorry?
That doesn't follow from what you just said about.
So I mean, like realizable by vectors.
But the description you just told us of taking the diagonal and truncation.
Oh, so you need to do slightly more stuff. Yes.
So is that over the same field or?
If the field is small, you might need to pass through an extension. But in characteristic 0, it would be over the same field. And then there's just like another, this is a kind of a cute example that Alex and I did, which is that if you were to take the diagonal Dilworth truncation of a Schubert matroid together with an opposite Schubert matroid, then in fact you get a Richardson matroid. And the definitions of these I don't want to give, but it's a beautiful and suggestive result. Okay, so here's the like a key piece of intuition, which is that the rank of the diagonal Dilworth truncation of M1 and M2 is bounded above by the rank of M1 plus the rank of M2 minus 1. Okay, so in particular, right, if M1 was just the uniform matroid of rank 1, then I would just get the rank of M2. And so, yeah, if the situation in the first proposition is typical, and Alex and I say that that D has expected rank if that's an inequality. It ends up being an important hypothesis for us. If, on the other hand, the inequality is strict, then you can actually realize D of M1, M2 as D of M1 with the truncation. So this is the normal truncation of M2, which is an extremely strange and very non-symmetric thing to do, but it's true. You can actually truncate either of them. Okay, so here's an actual example. So on the left, I've got the Fano matroid. On the right, I've got the non-Fano matroid. It turns out that in both cases, the diagonal Dilworth truncation of the matroid with itself is uniform of expected rank. So it's going to be uniform rank 5 on 7 elements. And we can kind of talk through and see that, so if it's uniform of rank 5, then every 6 element subset should be a circuit. So what do I need in order for that to happen? I would need, for example, the set 1, 2, 3, 4, 5, 6 to be a circuit. So I need it to be, its cardinality to be equal to twice its rank in either the Fano or the non-Fano. But every size 6 subset spans the Fano or the non-Fano. And then you need to check that no smaller subsets possibly satisfy this condition, which is true. Okay. So yeah, there's it doesn't seem to be terribly sensitive operation. Oh yeah.
I think I'm missing something. The F is realizable for characteristic 2, but the uniform 5-7.
Yeah, that's fine. I mean, this is a construction on matroids. So
I thought if M1 and M2 were.
that also is no big deal, right? I mean, you can have them like you will. Right, what it's saying is that U5-7 is realizable over the common field, or sorry, realizable over either field, and that's not a contradiction.
This is a place where you need to extend your ground field, right? U6-7 is realizable.
Yes, that's correct.
Realizable over F8 or something.
Yeah. So like just assume like algebraically closed field. Okay, so. Okay, we're nearing the end of the first construction, and this is the key to making the second construction. And it says that if you have a circuit of D, it can be written as a disjoint union of an independent set from M1 and an independent set from M2. Okay. And right, so let's think about this for if one of the matroids is uniform of rank 1, then you're just saying a circuit can be written as an independent set from one of the matroids plus one additional, which is true. So what you can do is you can try to fix a coherent way of breaking the circuits of D. So you want to have a coherent way of breaking all the circuits of D. What I'm going to do is I'm going to look at all the decompositions of a circuit as I1, I2, and then I'm going to take the lexicographically first such decomposition. So I'm going to call this the initial decomposition of the circuit. We saw for the Fano and the non-Fano that the diagonal Dilworth was the same when you did D of FF or D of non-Fano. However, the way that you break the circuits is different for these two. So let's just focus on this bottom or this circuit right here. All these circuits end up getting broken the same. But if I were to look at the circuit 1, 2, 3, 5, 6, 7, then in the non-Fano, I can break that as 1, 2, 3, disjoint union 5, 6, 7, because 1, 2, 3 is independent in the non-Fano and 5, 6, 7 is independent in the Fano. However, 5, 6, 7 is dependent in the Fano. So this way of breaking this particular circuit is no longer valid for D of for the Fano matroid, and so I need to use a later decomposition of this circuit, and so I do 1, 2, 5 disjoint union 3, 6, 7. Okay, so although the diagonal Dilworth truncation was not super sensitive to the input matroids, the way that you break the circuits is super sensitive to the input matroids. Okay. This is, I suppose, part of the second construction. So, given a basis of the diagonal Dilworth truncation and an element not in that basis, you can add the element into the basis and you get a unique circuit, just like that unique circuit has an initial decomposition. And I'm going to call the element that I added in externally active if it was in the I1 component of the initial decomposition of that circuit. So yeah, this is like a generalization of external activity to any pair of matroids. Here's the example when one of the matroids is uniform of rank 1. So in that case, the diagonal Dilworth is the other matroid. And so how do I break a circuit in this case? Well, I need to look for the lexicographically first way to write it as a disjoint union as an independent set from one n and an independent set from the other thing. So what I'll do is I'll just take the minimum element of that circuit as my I1 and the C with that minimum element deleted as my I2. So in this case, the notion of external activity that I just described is like the super classical notion that was like introduced by Hutt and probably goes back to Whitney and his study of broken circuits, just writing the formula for the chromatic polynomial graph. So here are some results about external activity in like what I would call the classical case, right, where one of the matroids here is uniform of rank 1. And so if you look at the generating function that records how many bases of your matroid have a given number of externally active elements, it turns out that that's an evaluation of the Tutt polynomial of the matroid. It's T1, well, it's Tutt at 1T. And the coefficients of this polynomial form a log concave coefficient sequence, and that's due to Ardilla, Deneb, and Hutt. If you were to look at the collection of all bases of a matroid that have no externally active elements, then this gives one of the first examples of, well, sorry, that's not true. It gives an important example of a shellable simplicial complex. This was proved by Provin in the late 70s. Okay, so here's like a first result that Alex and I have, which is that if you have just a pair of matroids in the sense I previously described, and you look at the sequence that counts the number of bases of the diagonal Dilworth truncation that have exactly k externally active elements, then it turns out that that sequence is a log concave sequence. I've got an example down here. If both the matroids were uniform of rank 2 on 4 elements, then the diagonal Dilworth is uniform of rank 3. And this sequence of externally active or of like external activities is the sequence 2, 2, which is indeed, well, I guess log concave doesn't even make sense here. In any event, there it is. And but this does show something important, which is that this generalized external activity is not normal external activity, because if it was normal external activity of some other matroid, then you would get a 1 showing up in this sequence. And this is kind of a silly remark, but when you get a symmetric sequence when the 2 input matroids are equal.
Is corank the largest possible number?
Yeah, corank of D. Okay, so the spoiler, like how does this come about? This it turns out that this ends up being the intersection numbers between 2 churn classes of 2 different tautological quotient bundles, and so in this case the log concavity actually follows from our result in the joint paper with Chris and Dennis and Hunter. Yeah, I guess the contribution of Alex and I here is that we computed like a combinatorial formula for what these intersection numbers are. So in any event, this notion of a generalized external activity is showing up in like doing computations of intersection numbers on a Berget variety. Okay, so this is the main player of the talk, the external activity complex of the pair of matroids. And I promise that this thing is going to be worth it. So it's going to be a simplicial complex, and it's going to have vertices that come in 2 flavors, some x's and some y's, x1 through xn and y1 through yn. Its facets are going to be in bijection with the bases of D. Okay, so 1 facet for every basis. And what's going to happen is that, so here I've used like a monomial to describe the facet. And so what you can think is that if I have a subset down here, then I take the product of all the xi's that are indexed by that subset, and likewise for the y's. And then to get the rest of the faces of the simplicial complex, I should just take divisors of these monomials. So sufficient to just write down a list of monomials to describe the complex. So on the x's, you're going to record a basis of the diagonal Dilworth together with what elements were externally active for that basis. And on the y's, you're going to write down that basis together with what elements were not externally active for that basis. It feels like redundant information, but it's all absolutely necessary. Okay. So this is a weird thing to write down. In the case that one of the matroids is uniform, it turns out that this was introduced by Federico Ardilla and Adam Booker, where they called this the external activity complex of a matroid. And this was later studied by Federico along with Castillo and Salmar. Let's try and get a feeling for what goes on with these things. So if I'm going to take both the matroids to be uniform of rank 2, so that D is uniform of rank 3, then the ground set of my simplicial complex will have 8 vertices. There's going to be 4 facets that have cardinality 7. And so I'll just do one of them slowly. So if I look at the basis 1, 2, 3 of D, then I need to ask, is 4 externally active? What do? I add 4 in, I get a circuit, 1, 2, 3, 4. That's a circuit, 1, 2, 3, 4. And then I need to decompose it as an independent set from the first matroid, union an independent set from the second matroid. But that decomposition is just 1, 2, disjoint union 3, 4. And so was 4 in the first component? The answer is no, which means that there's no externally active elements here. Okay. And so that means that the monomial that corresponds to this facet is exactly the same. So you can see in this way that so if I were to try to add 3 into this basis here, then I would find that it was not externally active, but the last 2 bases have a single externally element. Right, so this is the simplicial complex. It's kind of a beast. It's a cone though. Many of these facets have like the same monomials in them. And so if I decone the simplicial complex by removing all of those cone points, and then I can give, so here's a picture of what the geometric realization looks like. I mean, these are pictures, but I haven't learned anything by looking at these pictures.
On the edge from X3 to X4 twice.
Oh, really? Oh, okay, yeah. Well, you're learning even less now.
Oh, so is that actually the valid way to culture? You good?
Yeah, probably. Now I feel unconfident, so let's move on. Now to the last, I was like, I should draw a picture of this thing, and evidently I drew it wrong, so there you go. Here's the theorem with Alex. Okay, so there's 4 parts to the theorem. The first thing is that this simplicial complex that I just told you, the external activity complex of the pair of matroids, is a Cohen-Macaulay simplicial complex. Secondly, the finely graded K-polynomial of this thing is bivaluative. So I'm going to explain each of these parts in just a moment. And the third part, so this is the part that connects the external activity complex to the second motivational problem. It says that if the diagonal Dilworth has the expected rank, then you can actually write down a formula for what the Z2 graded K polynomial is. And it turns out that it's the generating function for the Euler characteristics of these tensor products of exterior powers of dual quotient bundles. This last part of the theorem allows us to say that if you look at the terms where the 2 indices on the exterior power add up to n, then it turns out that the sign of that Euler characteristic is -1 to the rank of the diagonal Dilworth. And because of this, we're able to provide like the missing link that allows us to say that Speyer's F vector conjecture holds.
You get sign definiteness for all these?
I mean, it appears to alternate in sign, so it's got like K-theoretic positivity, but we can only pin down the sign for the terms where I plus j is equal to n.
Doesn't that problem the Cohen-Macaulayness?
So no, that actually would improve. That would prove sign alternation for the Alexander dual. Okay. I'll have a word on this at the very end. Okay, so I don't assume that everybody here knows what a K polynomial is. So what is a K polynomial? So here's if you have a simplicial complex on vertex set x1 through xn, then the finely graded K polynomial is some generating function for the facet. So you're recording what's in a facet, what's not in a facet, or sorry, what's in a face, what's not in a face. And you need to do this over all the faces, not just the facets of the complex. Okay. And so in general, when you expand this polynomial, there's going to be like tons of cancellations and lots of alternating signs. Okay, so this is the finely graded K polynomial. Because you're remembering exactly what occurs, which vertices occur in a particular face. Okay. The Z2 graded K polynomial. So this is something that shows up when you've got like vertices of two flavors. And so here I've got this differential complex that's on vertex at x1 through xn and y1 through yn, just like the external activity complex. And then the Z2 graded K polynomial is going to record how many X's show up in a face and how many Y's show up in a face, along with 1 minus how many X's don't show up in a face and 1 minus how many, or v to the number of Y's that don't show up in the face. Okay. So this is a specialization of the finely graded K polynomial. And it just records less information. Okay, so that's that's two of the objects that show up in the main theorem. What does bivaluative mean? So what you want to do is you want to compute the K polynomial or the finely graded K polynomial associated to two matroids. And so I drew both of them as U24 here because they're the only things where I can draw pictures that with a nice subdivision. And so what happens is that you want to compute this K polynomial, but this thing wants to subdivide into the pyramid on the top plus the pyramid on the bottom minus the pyramid in the, or sorry, this middle. And so does the thing in the other argument of the K polynomial. Okay, so you've got two matroids they want to subdivide. And so to be bivaluative means that you can do kind of inclusion, exclusion on each individual factor. So I get the, so I get the K polynomial where I keep the matroid on the right fixed and I expand the matroid on the left as the pyramid on the top plus the pyramid in the middle. And then I also need to be able to do that for the other argument of the K polynomial. Right, so this is bivaluative. I trust that you can fill in the details for a more general case. Lastly, what about co-Macaulay? Hey, so co-Macaulay is like a tricky thing to motivate for people who haven't seen it before. So there's an algebraic definition which says that a complex is co-Macaulay if it's Stanley Reisner is co-Macaulay over a field. If it's Stanley Reisner ring over that field is a co-Macaulay ring, which means that its depth is equal to its codimension, which means something about the minimal free resolution of this thing. There's a topological description here. And it says that so a complex is co-Macaulay means that it's homotopy equivalent to a wedge of spheres. And furthermore, the link of every face is homotopy equivalent to a wedge of spheres, which means that the homology of the links of all the faces vanishes except in top dimension. In combinatorics, there's no pure analog of what it means to be co-Macaulay, but there are strengthenings that imply the co-Macaulay property. The most common is shellability. It implies co-Macaulayness, which means you can build the complex up one facet at a time in some kind of controlled way. And then even stronger than that, there's vertex decomposable, which is a very strong condition that implies shellability. So here I conjecture that the external activity complex of a pair of matroids is shellable, and furthermore, it's vertex decomposable. It's pretty strange. So first of all, in the case when one of the matroids is uniform of rank 1, this was proved by Ardila, Castillo, and Sampar. But they showed shellability, but they did not show, they showed lots of shellings actually, but they did not show that it's vertex decomposable. And I should just point out that like for as combinatorialists, you should be like bothered by the fact that I'm able to show that a simplicial complex is Cohen-Macaulay. Like a big class of them is Cohen-Macaulay, but I can do it via algebra only. Like this, I mean, I don't know, but I feel like this doesn't happen in combinatorics very much. We've got like one tool to show shellability, or sorry, Cohen-Macaulay, and it's like shellability. So this is surprising to me. Okay, so here's recapitulate the theorem that I've got the external activity complex is Cohen-Macaulay. Its finely graded K polynomial is bivaluative. If I coarsen to the Z2 grading, I still get something that's bivaluative, but now I get this beautiful expression for what the K polynomial is. It's a generating function for Euler characteristics. And furthermore, the last term in this K polynomial, I can tell you what the sign associated to it is. Okay, so here's a quick example so if you were to do the uniform, M1 and M2 are both uniform of rank 2, then the external activity complex has 240 faces. And it turns out that there's tons of cancellation in that formula that I worked down. And the Z2 graded K polynomial just becomes 1 minus U squared B squared. So there's like some simple consequences that you can derive from these theorems that give you formulas for what these Euler characteristics are in some like special edge cases that so some of these are known. If the rank of the matroid is half of the size of the ground set, then you can say that the Euler characteristics are going to vanish unless you're in two very specific cases. And in those cases, you either get 1 or -1. If twice the rank of the matroid is the size of the ground set -1, then you can get a formula for some of these like top exterior powers of two quotient bundles. You end up getting a beta invariant divided by 2. Which is kind of weird and surprising. I don't know how to generalize either of these results. But I do have another result, which I'll talk about in just a moment here. I wanted to explain how to get the fourth element or the fourth item in the theorem using earlier parts. So this is like a sketch. But the fourth part of the theorem gave you the sign of the Euler characteristic. Okay. So what you do is the following. So you look at the minimal Zn graded free resolution of the external activity complex. So this is the Zn graded means that you can't tell the difference between the X's and the Y's. You just remember whether you had an Xi or a Yi. It turns out that that is the same as, in like a precise sense, the finely graded minimal free resolution of the independence complex of the diagonal Dilworth. This turns out to be intimately connected to the delta being Cohen-Macaulay. Now the minimal free resolutions of independence complex of matroids. This was studied by Stanley in the early 80s, and he just gives you a formula for what the Betti numbers involved in these things are. And he tells you that the terms of total degree n can only come at the last step of the free resolution. And therefore, you actually know the sign that with which the terms of total degree n will be in the K polynomial, which is recording what's happening in the Betti solution. All right, so if you use part 3 of the theorem, which said that the Z2 graded K polynomial was telling you the Euler characteristics, and you chase everything around, then you find that term, those last terms in the K polynomial had sign given by -1 to the rank of D. Okay, so this is obviously like a super sketchy, but we can say slightly more here. That this quantity, these Euler characteristics, so the signed Euler characteristic is actually equal to a sum of dimensions of some reduced homologies of links inside the external activity complex. And the proof of this result, going to Matt's question earlier, is not immediate from Hochster's formula for minimal free resolutions of or for Betti numbers of simplicial complexes. Instead, you need to use the theory of extremal Betti numbers and then apply Hochster's formula to the Alexander dual. So in any event, we've got like now an extremely nice formula for what these Euler characteristics are. And yes.
What do you mean by the theory of extremal Betti numbers? I mean, I know these are Cohen-Macaulay, so you only have one extremal Betti number, but then what do you?
So there is multi-graded extremal Betti numbers. Yeah, so they like in the original paper on extremal Betti numbers, they do a whole multi-graded theory. And yeah, so it turns out that the Betti numbers that I'm interested in are extremal in that sense.
Thank you.
Okay, so it turns out that when both the matroids involved were realizable or a field of characteristic 0, you can replace Euler characteristic with a single higher cohomology group, and all the other higher cohomologies must vanish. Okay. So this uses some results of Jerzy Weber for what the minimal free resolution of the complex will look like. Okay, so I'm out of time and essentially done. This is the last slide. So how do you prove these results? This is what the next talk will be about. You study what we call like a Schubert variety of a pair of linear spaces, which will be some subvariety of P1 to the n. And it turns out that this thing Grobner deforms to the external activity complex. So this allows you to do a bunch of geometry and then transfer that knowledge to knowledge about the external activity complex. The hard part, I mean, so that's not easy, but the truly hard part is extending these results from realizable matroids to all matroids. And so this comes from computing these products of Chern classes using a kind of refined tropical intersect. And so that's all I have time to say. Thank you all for listening to me.
Questions for Andrew?
I just have a simple question. Does your Dilworth thing have anything to do with the Dilworth theorem? Is that related?
Well, now you're just like exposing my my memory of my dread combinatorics, which Dilworth theorem.
Was that the smallest?
Oh, like it's like chain decomposition stuff? No.
No.
Yeah, thank you for the talk. I mean, it was amazing. I have one question. So you proved this Cohen-Macaulay via algebra method. So that tells you that the H vector is the negative of this complex.
Yeah.
Have you computed this for some examples? And do you have like
I sent like 4 of them to Matt yesterday. I have, but I don't know too much.
But do you see any patterns in that H vector? Like I don't know.
Oh, not discernible, right? Well, I mean, so it should come from the shelling, right? So I do have some ideas about what should be going on with the shelling. I just can't prove them.
Okay.
There's something in your blind spot, Sam.
Thanks. So using your bivaluativity then, is it enough to compute all these things for Schubert matroids?
Yeah, but it turns out that doesn't make it actually makes it worse. Because then you need to be able to compute all these invariants like exactly for Schubert matrix, and you don't, because it's not as good as you'd think, and because the bivaluative group, it's spanned by pairs of or like tensor products of Schubert matroids. But you need to take Schubert matroids with respect to, like, you need to be able to vary the flags for both. You can't fix the flag in one and fix the flag in the other and only look at those. You have to look at all pairs of different flags. So it doesn't help at all.
So that's not easy then to look at.
No, it's because then we said what happens when you do a Schubert and an opposite Schubert. And I think Luis's paper on the Speyer's invariant sort of tells you what to do for a Schubert and the same Schubert, but in general, like it's probably just some random mess.
You said a lot of good things happen when the rank of the Dilworth Matroid, some of the ranks -1. Do you know how often this happens?
So I think that Luis or David might be able to say something slightly better about this because they've got this notion of like so let's just focus on like D of MM. So that will be expected rank, which would be twice the rank of M minus 1, provided that there's not like an overly crowded flat or hyperplane inside of the matroid. So there's perhaps a combinatorial characterization of, but you should expect in general that D of MM is ranked twice the rank of M. This captures most cases.
Matthias?
So you could change the vector bundle like S or Q without changing the K class into a sum of line bundles, and this should not affect the Euler characteristic results, but may affect the cohomology results. And my question is, should one at all think about those vector bundles as sum of line bundles, or is it like a bad idea to go there?
I think it's a bad idea. It should destroy the entire approach. So the entire approach is predicated on the fact that the bundles that we need to study are sub-bundles of a trivial bundle. And so now you're going to have bundles that, if you look at the sub-quotients that come by the like filtration of the SL or something, you're going to get things that are neither globally generated and nor is there dual globally generated. And that's just like, that's the worst possible case to be in.
I'll say 8 years ago back at the Fields Institute, Alex Fink, Chris Shaw, and I computed a bunch of those and could not find any pattern in the signs.
Yeah.
Do you have calculations on Schubert functors? I mean, if you tensor problem is budget, the sums of Schubert functors.
Yeah, so I don't have any like explicit calculations. I mean, I would like to see that, but I don't know. It's probably harder, even stuff.
Okay, well, let's thank